And I'm really happy to invite Jordi from Polygon to the stage. Thank you so much for coming. And Jordi will speak about infinity scalable proof. Okay, cool. Thank you.
Hello? Yeah, let's start here. I'm gonna need this because this one? This one.
No, he wants the mobile
I prefer this one because I'm gonna.
Okay, mic is off. The microphone.
Okay. Hello.
Yep.
Yep. Hello. There we go. So, when we're building a proof, what's the biggest limitation that we have? If we want to build a single proof, this is, for example, the structure of a ZKVM proof. You can understand that as lots of polynomials, very huge. In general, in the case of the ZKVM, we're working with 2 to the 23 degree. Actually, we are going now to 2 to the 24 or 2 to the 35. And you cannot go much farther than that. For many reasons. Well, you have some hard limitations. For example, it's difficult to go to the 32 because the duality of the prime fields that we're working is, in the case of the Goldilocks, it's just 2 to the 32. But also there are other limitations. Memory spaces, you need to do entities of very big polynomials. So it's what you can prove in a single proof is quite limited. Okay? And the other big limitation is that, okay, you build a proof, you know how much it's going to take. In the case of the ZKVM, this takes a couple of minutes, more or less, in a big machine to build. But you have certain numbers of operations or that you can do there. If you have a ketchup state machine, you can do maybe 2,000 ketchups, or you can do many arithmetic state machines, but it's a fixed number. Okay? And this is hard to scale because sometimes you want to prove things that are more variable. The Ethereum block can be, you can have a lot of pairings that you want to prove, or you want to have, or maybe there is a lot of ketchups, or maybe there is a lot of arithmetic operations, and it's very variable what you want to do. And the problem of this structure is that you end up wasting a lot of area. Read it as a proving time or optimization. It's just if I can do 2,000 ketchups, and if I'm doing only 1,000 ketchups, that means that there is like 50% of this state machine that's unused, that's wasted. Okay? So how can I fix that? How can we do? Well, here the main idea is to use recursion. Okay? The idea is instead of doing one single proof, I can divide the problem in doing many proofs and then using recursion to actually aggregate those proofs. So if I need, in this case, for example, if I need a lot of binaries, because in the case of proving this proof, I need a lot of binaries, what I can do is I can generate a lot of binary proofs, and then I aggregate them together, and at the end, I'm aggregating all the proofs to a single proof. This is the concept of VDCPs, or Variable Degree Composite Proofs, that we are just dividing the proof in many subproofs, and we are aggregating them together to compose to get a single proof. The big problem, and this is very much what I want to explain in this presentation, is how we connect each proofs. Because, here, for example, in the case of the main state machine, maybe here I'm using many arithmetics. I'm assuming that many arithmetic operations of cross prime field, for example, or different, or binary operations. So I'm assuming that those operations are valid. But then some other state machines needs to prove that actually those binary operations are correct, or these arithmetic state machines are correct. So how do I link one subproof to other subproof? Okay. So here the solution is very much the lookups. Okay. And to explain the lookups, well, let's start. This is the basic, the typical. I'm not gonna go deep here, but this is the standard polynomial commitment schema. This is very much how it works. So the idea is you have a prover and you have a set of polynomials. You commit to these polynomials. the verifier sends some challenge, and then you just open these polynomials at a certain point. You just verify that some polynomial equations, some polynomial identities follow at this point, and for the Schwarz-Zippelman theorem, you can assume that then the full polynomial is correct. So with a single verification in a single opening, in a single point, in a single random point, you can prove that all the polynomial is correct. So in a single proof, maybe you can, if the polynomial is 2 to the 32, then you can do like 232 checks at a time. And this is the nice thing of Starks for itself. Okay, so this is the basic operation. And then the idea is, one of the basic things is we want to do lookups or permutation checks. This is the basic thing about the permutation check. So how the permutation check works? Well, here you mentioned that we have two polynomials, one polynomial f, another polynomial t, in this case of this degree 3. So we have two evaluations, 3, 2, 4, 1, and this is 1, 2, 3, 4, okay? And we want to prove that these two polynomials, so we come into these two polynomials and we want to check, we want to prove that that one is the permutation of the other, so that all the numbers here are here, but in different order, can be in different order. So what's the schema here? So we have these two polynomials. So the first step here is we commit to these two polynomials, f and t, okay? Then here the verifier just send a random challenge, a vita, okay? And then the prover we built the polynomial z. We call it this is the grand product. This is the grand product polynomial. We will see later on that we call it the boss. Okay, but this polynomial z mainly what it does is well, the first one I'm just putting in the numerator. I'm just taking these three here. I'm just putting in the numerator plus beta. In the t part I'm putting in the numerator. The next one I'm just taking the previous one and multiplying by the ones in this row, 2, 1, 2. See here, this 2 goes here to here. Then I'm taking the previous one and I'm multiplying for 4 and 3, and the previous one I'm multiplying by 1 and 4. Okay? So because I'm just took all the values here and I took all the values here, all this formula, of course, the numerator are in different orders, but the numerator and the denominator is the same. So the last row needs to be 1 if it's really a permutation. If f and t is a permutation one each other. Okay? So the polynomial equations for checking this is that L4 is just a constant polynomial. It's a polynomial that's just 0 everywhere except for the last column. And then you say that if L4 is 1, so in the last column, z minus 1 needs to be 0. Okay? If not, this will hold. Okay? But so that means that z needs to be 1 in the last column. This is the first thing. And the second thing is that the other equation that we are doing here is how we are composing this. Actually, we are taking z prime. Z prime means the next one, the next row. So how I'm constructing this next row? Well, this next row needs to be the previous one, the z is the previous one, times f prime plus beta. So f prime is the row that I'm building, plus beta, plus t1 plus beta. Okay, so this is the equation. You see, this goes wrong. So if you go, if in the last moment, the next one, this is going to be the current one, and the next one is going to be the first one, but the current one is 1, so z is going to be 1, so the first one also holds. Okay. So in the structure, so I'm sending beta. Here I'm building this z polynomial with beta. I'm committing to z, and then I'm just doing the normal polynomial commitment. I'm just taking a random opening point. I just do all the openings, and I'm just checking that these polynomial equations are valid. Okay, so this is the way how range checks works. Okay, normal range checks work with multiplications. Okay, the interesting thing is that I can do exactly the same that I did before, but instead of using multiplications, I can use additions. So how I do additions? Well, here instead of, so I'm just taking, let's take here for example, I'm just taking the previous one, so what I have in the previous one, but instead of multiplying something in the numerator and dividing something, what I'm doing is I'm adding something and subtracting something. And what I'm adding and subtracting? Well, I'm just adding f prime plus beta, and 1 over f prime plus beta, and I'm subtracting 1 over t prime plus beta. So in the last row, Okay? So because I'm adding all the f's and I'm subtracting all the t's, when I'm, instead of doing what, this is 0, okay? Because I'm adding and subtracting something. Okay? So I'm just doing exactly the same, and this same trick works. Of course, I cannot use the numerator. In order to work this, I need to use the denominator, but this is what's known as lookup. I mean, it's looking from logarithmic, I'm converting multiplications with additions, but the cool thing is that I'm also converting exponents with multiplications, okay? So with this lookup, I mean, we can do the same with the same structure with multiplication. There is another trick that I want to show is like, okay, when I have a lookup, of course, if I want to do it with multiple columns, I just do a normal random combination. So I just send like another challenge. In this case, it's alpha, and instead of using with f and t, and you can have f1, f2, and ft, and then just doing a normal linear combination of f. Okay. So I can do a permutation check with different columns. Okay. But the cool thing of this lookup is that the cool thing of this lookup is that I can have here an extra column. So in the right side, an extra column I can have is like how many times this appears to the left. So instead of doing a permutation check, I can do just an inclusion. If I want to see that this is, so how many times this row appears here. So the row 211, how many times here it appears? Appears 1. The row 422 is 422. This is wrong. No, the 422 appears twice. Okay, so I can put this polynomial to 2. I mean, this is the number of times that this appears. And then I'm adding or subtracting the number of times. So in the right side, I'm subtracting the number of times that this appears. So this allows me to do not only permutation checks, but allows me to do lookups on that. And I'm just doing lookups, just adding or subtracting something to this z polynomial, or if you want to this boss polynomial. Okay? So when I want to connect, so I have this kind of column, we call this z column, that I can add things and subtract things to this column, to this z column. So the idea is that I can have different subproofs. Okay? So I can have built a system with 2 different subproofs, maybe with different size like this, each one with its own z column. Okay? And I'm just taking the last row of this column, which is actually what sums up. So everything that sums up, okay, and take that as a public input of this subproof. And then the wrapper, the prover that actually prove the 3 subproofs, can just take these public inputs that you are proving, add them together and check that these are 0. So with this structure is super interesting because it allows me to send things to the bus. So it's like maybe a main state machine can say, I'm assuming that this arithmetic operation is valid. And then there is another state machine built in another subproof that say, yes, this thing that's assumed, I am proving that this arithmetic state machine is, this arithmetic operation is correct. So one is adding something to the bus, and the other is subtracting to the bus. And I'm just checking that whatever I add to the bus is subtracted to the bus. And what can I add to the bus? I can add anything. And the idea is that I just need one single bus. For example, imagine that I have arithmetic operations, binary operations, storage operations. The idea is like, because using the multi-column, I just can take the first column and just putting a constant, depending if I'm doing maybe one of those functions. If I'm doing an arithmetic, if I'm doing a binary, or whatever I'm doing. So I'm just taking maybe the first column just taking the first column, and what I'm adding to the bus is something plus a column. So I'm just using a single bus. One thing that I can add, for example, with this is, for example, a range check. When I'm doing it in the range check, I'm just adding something to the bus. And this is free, let me say free, it's not free, a rate check, but I can have a single arithmetic state machine with the rate checks and with just the C. There's going to be a higher C, but this C can be relatively low, and so this C can be relatively low, and so it's what I can amortize the cost of the rate check. I have a single rate check, and all the state machines that are using rate checks can just reduce this, can just send these things to the bus. Okay. Also, another interesting thing of the bus is what we call it the public tables. Public tables is, okay, in this bus, so the verifier actually is just, the verifier of this subproof is just it's just assuming this and it's saying that this is equal to 0. But the verifier can also add things here. Instead of being 0, I can, for example, add operations. So, for example, one thing that you can do in the memory, so in the memory you can, for example, do a read, final reads, and then these reads. So you just add that to the bus. But instead of being another state machine that's subtracting to the bus, the same verifier is really adding these reads. The verifier is adding these reads, is computing these, because the verifier has the challenges, so can add things to the bus somehow and check that this is also proven there. So it allows me, for example, to do public inputs, a lots of public inputs from the verifier easy. Okay, so this is what was called the public inputs. So this is in the context of the Polygon CKVM. Of course, this allows us to remove all this idea of counters. This allows us to build anything, and it also has a lot of optimizations here. Okay? But the most interesting thing is that it allows us to build systems very much like that, the same way that we're building some whole hardware. We can have different different components. You can see like electronics, and we connect them to the bus. You can have a component that's just doing arithmetic operations, or a component that's doing catch-ups, or a component that's doing some storage operations, some specialized operations. You just connect them to the bus, and then you just join them together with these backlogs. These are some examples of some interesting things that you can do. For example, if you want to do you have a processor and you want to do a memory, you have a memory aligned operations. You can have a memory that's doing very well for doing when you are doing operations with mem aligned operations. But the thing here is the bus is sending, when you're sending this, the arrow up to the bus is just adding something to the bus. Okay? So the processor can just do, okay, I want to do a read, but this is a non-aligned read. Well, I can have an intermediate state machine, we call it mem-aligned, that actually is just converting, in one side is just subtracting from the bus, it's solving from the bus this read from the processor, but maybe adding two other reads, because maybe one mem-aligned, maybe needs two reads, two aligned reads to there. So it's sending that two aligned reads to the bus. And then the memory is just absorbing, the mem-aligned is just doing the normal two mem-aligned operations. But from the processor perspective, it's absolutely transparent. They are just doing one memory operation. You can have, let me just go to here. You can have, for example, for the arithmetic state machines, I can have one 32 bits and another 34 bits processors. The processor is just sending arithmetic operations, and depending on the operation, maybe it's just using one arithmetic or one state machine or the other state machine. So it allows me to actually use very well it allows me to use very well the area. The proving cost of that. I'm just solving everything that I want to prove in the right way. Okay, so this we'll see that every time we'll have more specialized operations in order to optimize the provers itself. Okay? Another interesting thing is, for example, for continuations. So when I have, for example, a processor, the processor at the end is, okay, I have a processor, then I go to something like a sleep mode, I just stop, and then I have like another chunk of the processor that needs to continue. But I need to transfer the current state of the processor, and have registers, and what are the registers of them, we need to continue at the same point where I was before. Well, what I can do is, at the end of a chunk of a processor, I can just send the state to the bus and recover that state in the first line, in the first instruction, the first clock of the bus. Okay? And maybe in the last one, I'm just finishing that by just resetting the processor at the end, and then you go to the first one. Okay, so you can have this idea of continuations. The same thing for the memory. The memory, the thing is that you don't split that. In the memory, you don't split that by timing. I mean, you don't do like by clock, but you split maybe by address. Okay? You can have one state machine that's proving all the reads and writes that happen with a certain address, another state machine that's happening to the certain address, and the other is a certain address. And if you understand this memory state machine as a state machine, you can save the state and recover the state again. So it allows me also, for example, to split the memory in different chunks. Okay. And yeah, you see it's important you see this flexibility and how powerful is this concept of having a bus, okay? But how we build that? I mean, the idea is from the engineering perspective, I mean, this is very nice, but in the engineering perspective, how we build all these systems, okay? And here is the importance of this PIL2. PIL2 is a polynomial identity language. 2 is because it's a second version that we are doing with PIL2. PIL1 was done by the ZKVM, and with all the learnings that we get from this language, and mainly to use the VDCPs, I mean, to have to be able to define these different airs, different subproofs that can be joined them together, okay? And how these and being able to build a single prover, a single tooling that allows you to write arithmetization and then prove it with Starks or with any other prover. Then we use this PIL2 language, and this is very much what we are working for this. Okay, these well, these are a little bit the advantages that has this language. But at the end, when you have a PIL2 arithmetization program, at the end you see all these polynomial equations there, and the idea is that in a relatively simple readable text file, you can understand all this arithmetization. So it's a specialized language just to understand what actually you are doing, instead of mixing it with other higher level languages. And this is very much thing on that. And it allows us also this composability. I mean, the idea of this PIL2 is that this modularity of having different having an arithmetic state machine, and this can be reusable in any proving design. Or you have a ketchup state machine, this is reusable. So the idea is, depending what you want to prove, depending what you want to build, you will be able to pick up any of these libraries and connect them together somehow. Okay. The other big advantages, and I think this is probably the most important thing. The fact that we are dividing the proof in these relatively small proofs, these relatively small subproofs, this allows us to build the proof in a more parallel way. So this allows us to have, so instead of having a single machine, a single huge machine that's building the proof, this allows us to have a network, or if you want a cluster or a supercomputer or whatever computation of provers or computers, if you want. They can be GPU based, they can be hardware specific based, they can just be CPU based. And the idea is that because I can divide the proof in many of these subproofs, I can divide this work in many of these resources. So this scales very well. Okay? So with this, with using this technique of VDCPs, of variable degree proofs, composite proofs, this allows us to, for example, to prove an Ethereum block with less than 12 seconds. Of course, the question is, and how many computers will you need for that? Okay, but because you can divide the proof very much and you can aggregate them very much, this is parallelizable in many computers there. So it's perfectly possible and it's perfectly achievable. Okay, so of course it's still a challenge, but this is with this structure. This is the goal, and this is where we are trying to achieve. Yeah, that's very much what I wanted to explain. I don't know if there is questions now.
So when you break down the proof into multiple parts, do you validate that the sum in the last row is 0, or do you validate some kind of combination of the sums?
No, we just, well, I mean, we are breaking these, we call it subproofs. Actually, they are not independent proof because they share the challenges, okay? But, so they share the challenges, but it's okay. I mean, it's one transcript, but many proofs. But in order to build the challenges, you need to take in account the other proofs' commitments somehow. So it's like you have like a single challenge. And because you have one single challenge, here is, and this is a little bit I mean, it's more a technical detail in how you build a proof. You have like, when you want to scale these things, you have like two techniques somehow, okay? So you can have like a lot of memory, and because I mean, even if you have a lot of them, you need to have many of them. So if you have a lot of computers, that's okay, because you just keep all the proof in memory, okay? But it's very cost intensive because you need to build you need to build this, you need to do the extension, and then you hash it, and then you get the hash, you get the commit, with the commit you get the challenges, and then you build again, and then you, at the end you get the queries, okay? So this is the structure. But you need to keep that in memory or somewhere because you don't know the queries until you don't compute everything in there, okay? You can do this way, but if you're assuming that you're computing the things twice, then no matter. I mean, okay, it's going to cost you twice, but the cool thing is that then the memory requirements are 0 or close to 0.
Yeah. So the verifier verifies each subproof and makes sure it's the same challenges?
Yes, I mean, so there is, exactly. So there is, actually it's like the challenges, so in the subproof, the challenges are public inputs set, so it's our public inputs of the verifiers, of the verifier circuits, okay? And then in the wrapper circuit, actually you are checking that the challenges that you are assuming that you are passing to the childs, I mean to the subproofs, are generated correctly. So because the hashing that you are considering, actually you hash them all together, and then you compute the challenge in the so the transcript is in the father in the parent, okay? And in the subproof you are passing it as a parameter for the verification.
About the 12 seconds, how many computers?
We don't know yet, but I don't think it's going to be many. But depending on, of course, depending on the kind of the block and it's a lot of parameters there. But it shouldn't be. I mean, it should be cheaper than what we have. It should be cheaper than what we have right now. And right now we're using one single big computer. It takes 2 minutes. One single big computer, it takes 2 minutes, and it's more or less 1/4 of a block. Okay, so it's like 8 minutes. Okay, so if you want in 12 seconds, just do the computations. But maybe I don't know, maybe with 50 computers, relatively not that big like that, maybe 50, 100 computers should be possible. But again, this needs to be done, and of course you need to all this aggregation part. I mean, the cost of the aggregations here, for example, all the work of Plonky for aggregating things is we're talking about milliseconds. So this is a lot of things that are, I mean, a lot of knowledge that it's in there, but we are just taking for that. But it's, and there are some, you know, the Windows computation of the things. I mean, there is a lot of tricks and a lot of details to get these numbers. But so my message here is that it's definitively possible to think about building L1 blocks, to proving L1 blocks in real time. Got the question there.
What connects the bus, is that what you call cross-table lookups in Polygon 0 paper?
Yeah, it's the Polygon 0 is lookups. I mean, you have all the I mean, I'm not a mathematician, and of course, do not take it that is not a proof. This is just to show you an idea, the idea how it works. Please do not this doesn't work. Okay, so this is just to explain the ideas, to explain how the things work. Of course, there is all the the serious work in the papers and all the proof of motivations. And yeah, there is the zero lookup paper that's explained.
Then another conceptual question: how far are we from using different proof systems across the bus? Let's say you do catch with Vinius and then the arithmetic tables with a classic proof system. Is that possible at all? How far are we from that?
But let's see. So in the bus, you can. So one thing is what you want to prove. The other is the proving systems that you're plugging in the back. Okay. So what you want to build in the proof. I mean, this is just a matter of doing the arithmetization of what you want to build.
Yeah.
I mean, if you want to build something, you want to work with a floating point. You want to prove some floating point operations. Well, you probably need to do some coprocessor, I mean some state machine to work with floating points or to do whatever you want to build on that, okay? Or use something generic that's going to be more expensive. The other thing is that from the abstract perspective, it's like, okay, you have a proof and you define the proof just by having subproofs, or subproofs or subA or Ayers. I mean, these are different Ayers. You have different Ayers that you have some equations that connects, I mean, these public input, these public outputs of each person, how you connect them together, and then you have all these polynomial equations. Okay, this is defined. This is arithmetization. Okay, but this arithmetization, it works with any proving. It should work with any proving any polynomial commitment-like proving system. If here you can plug a Starks like a proving system, which is mainly will work, but we can plug here a Plonk system like. Plonk is also working with that, or you can Plonk or any other polynomial, or maybe a bulletproof like.
So each subblock can be a different proof system.
It could, but I mean it could, but again, you will need at the end you need to join them together. So at the end you will need some sort of wrapper.
Okay.
Actually, I mean the strategy that we are following in general is we are using Starks everywhere. Here we are. Right now we are working with Goldilocks mainly, but again, it's we can switch there, and then at the end we are wrapping everything, and we are just using a normal Flonk to prove that on chain, just to produce the proof sites. That's the strategy that we're following. Okay, so that's the thing.
Thank you very much.